Welcome back to I'm finally reading my brother's book. I'm Clay Bascom, here with my brother, Dr. Gavin Bascom, theoretical chemist and author on the inside of a marble. In today's episode, we dive into the fascinating world of dissipative systems and friction. Two concepts that at first glance might seem simple, but actually open up profound questions about how the universe works. Is our universe a non-equilibrium or dissipative system, or is it a closed system in equilibrium? We'll explore how energy dissipation shapes everything from the tiniest quantum interactions to the grand movements of the cosmos. Gavin talks more about eggplants and ties all the previous episodes' concepts together to form a shiny new epistemology. It's a conversation that blends physics, thermodynamics, and a bit of philosophy as we ask what energy loss measurement tells us about the fundamental forces of our reality, and begs the question, are they really so fundamental after all? So let's get into it. Episode 6, Friction and Dissipative Systems. Looks! We are starting on Inside of a Marble. Something about quantum mechanics. Say hello, Gavin.
Hello.
Hello. All right, this week we're jumping into chapter 5, A Universe Far from Equilibrium.
Yeah, we are making it, and this is so cool to be this far into the book and still be talking about it, and have people still listening, and
I definitely have never made it this far into your book. It's very interesting. I have to admit that sometimes while I'm reading it, I get angry.
Oh, that's interesting.
Well, it's just I'll be reading it and I'll have to read it like 3 times in a row, and then I'll be like, oh, it clicks. Then I'm like, yeah, you could have easily said that in a lot easier language, just using your $10 words. But no, it's interesting. You seem to really focus in on friction. I like the friction.
Yeah.
Friction.
We'll explain that. But I'll say the reason it's hard to read is because it was hard to write. I also was struggling with these things, and I knew that there was like a little nugget of kernel of truth of something to get like to explain. And so just keep going at it like doggedly from all the different angles.
Yeah. I do think sometimes it was really more on my end that I was like, I should have understood that faster. But, I just didn't click because I'm not as used to the language as you are. And then there are times where you totally lose me, but I'm like, I think there was something there. But that's why we're doing the podcast.
That's why we're doing the podcast, because you can talk to me and ask about it. And then also sometimes it's just an image that will come back. And I think here's what I was gonna say. In this chapter, when I was writing this chapter, was the first time that I was like, okay, there's a book here. Like It took that long for me to be like, am I really saying anything here? And then finally it was like, yes. There's something really, really interesting and fundamental when I started thinking about it this way.
Get to chapter 5 of a book and be like, am I actually writing a book or am I? So yes, I will say that your enthusiasm in this chapter really comes through. There's a lot of exclamation points. There's a lot of italicizing. Like you can feel the energy, and sometimes you're like, oh wow, he's really onto something. I don't know what he's talking about,
he thinks he's onto something.
Definitely excited. So yeah, let's get into it. Let's talk about friction, infinite sinks. So I will admit, when I first saw the sub chapter heading was infinite sinks, I did picture like a bathroom sink. It was like
a really long, deep bathroom sink.
But you're talking more about heat sinks and
yeah, sort of,
or just like kind of like how
anything
dissipative, right?
Dissipative, yeah.
So an in equilibrium system.
Yeah, and I mean, you have to understand. Like, I was studying statistical mechanics, and that is one of the sort of fundamental features of it. So it was going to be the framework that I was going to use, the whole time.
Okay, so let's give it some framework. So you started to talk about thermal energies, right? Or you're talking about thermodynamics and energy transfer. So in energy transfer, equilibrium, systems that are in equilibrium, right? So my understanding is that basically means that there's no energy loss, or you can track the energy 100%, where all of it went. And then there's unequilibrium systems, or as you prefer to call it, dissipative systems. System the right word here?
Yeah.
Okay. And so a dissipative system.
Because it's not a single object. It's a set of interacting objects that. Yeah.
And so in a dissipative system, you have energy loss or heat loss. and that's considered basically goes into the sinkhole.
Right.
And it goes into the sink, it disappears, just like goes down the drain. Yeah. For some reason, that was important. I didn't quite fully wrap my head around that.
All
But
right.
you did link that to friction, which kind of was very reminiscent for me of the eggplant. I feel like there's some things going on there. Just kidding. All right, so let's go ahead. So,
The reason for the eggplant will be more in tune here a little bit, but
so it does tie in with the friction.
it does tie in with the friction, but not in any of that kind of way. All right, so basically, like when you are thinking about complicated sets of interacting things, you have to define the problem in a way that is it closed or is it open? That's another way of thinking about it.
Okay.
And in a closed system, everything is accounted for. All the energy is accounted for. It has to go somewhere. We know we can keep track of it all. And in an open system, it's like it can just siphon off somewhere and you can just, okay, it just disappears and it's gone forever. And, in some cases, one is more easy to calculate and one is not. And that just depends on a bunch of different factors. But I think most of us intuitively we understand what open systems are like more.
Right.
And friction is like the thing that makes this
When
easy
you
to
say
drive home.
open systems, you're talking about dissipative systems where
Yeah,
energy
things
is
where
lost.
like systems where things are allowed to go somewhere
Right. Because then
and just disappear.
most of us aren't keeping an accounting of the heat in a system, right? Like I use my oven and then I turn it off and I don't think about like, oh, there's still energy in there that needs to dissipate. It's not something that like,
Think about it more like when you go to stand up and you push down and the earth pushes back and you like come to a certain point
lost me.
where
I've never felt the earth push back.
Yes, you have. Every single time you stand up, that's what's happening. Like it's like in order to control your position. So okay, so there's a problem with in high school physics called the ice skater problem. And it's if you're out on a lake and there's zero friction, how does the ice skater get off the lake? Like, is it possible? And there's no ice skates, or ice skates don't work because there's no friction. So you try, and this is a problem for like people in space too, because there's no friction in vacuums in outer space, so there's no gravity. So if you're like far from the wall, how can you get off the lake?
Right.
Is it possible to get off the lake? What do you think?
Sure, you just go to the edge and cut off.
No, because whenever you take a step, you like slip,
you're
right?
stuck in the middle of the lake.
There's no friction. You're stuck in the center of the frozen lake,
and you have no momentum.
And there's no momentum. What can you do to get off? Is it possible to leave the lake? Or spit is the answer.
Yeah,
because you have to actually like
eject something with
mass.
you have to
eject something with mass. Something has to leave your system in order to create enough an acceleration. Right. And
is that why are people spitting in space?
I don't know. Probably. But I don't think that's how they get around. But that's how rocket ships work, is you have to actually, and this is the fundamental like limitation of rocket ships, is you have to carry enough fuel because you have to eject fuel in order to like physically eject something. It can't just be like smashing like a hammer or something.
In order to increase your acceleration.
In order to change your velocity. So, okay. So why do we care about friction? It's going to, hopefully this is sounding familiar by now, but basically this is another one of those situations where it's easier to think about friction as something relatively simple, which is like, here's the picture most of us have in our heads, or that you should have, of friction and why it works. If you like say it's your shoe in the ground and your shoe is made of rubber and the ground is wood or something. If you zoom in on the wood's got little jagged teeth. There's no like straight, shiny lines.
Mm-hmm.
There's like little jaggy mountains.
This is on like the molecular level.
At the molecular level, the rubber also has little jagged mountains. Mm-hmm. Whenever you like they go together, they like find, and then the more you push, the further those teeth like interdigitate. So this weird thing happens where the more you push, the more force there is sort of pushing back. And you could also think of it as like, okay, if I have one object and I have another object, the more you push, the more they become one object rather than two objects.
Mm-hmm.
In a very small molecular sort of representation. In order to calculate how to do that in a deterministic way that is, to use the language from the book, is concurrent and cohesive, like and contains all of the information and all of the different particles in terms of all of the fundamental forces, or like it would be a very complicated setup. Whereas what we end up doing instead is we say, I'm just going to approximate all that interdigitating and all that stuff that as like, it always is a force that pushes back and it gets harder the more you push down. So, and that works really well. And So there's just a term that's the surface area. Like if I have a bigger shoe, I get more force pushing back. And if I push down more, there's more force pushing back. But there's a problem with that approach because it depends on what your shoe's made out of.
Mm-hmm.
So now we have to say, okay, we'll put a little constant in there. We call it the coefficient of friction that just says rubber has a really high amount of force kickback and like water has a really low amount. So then rubber gets like 250 and like whatever. And that works. And the math works. But there's a weird, I don't know, if you're a physicist, that kind of a solution should make you uncomfortable
Mm-hmm.
because now I need a special constant for every material in existence to make my view of the universe work.
Right.
And so it worked well for rubber and it worked well for water, but what if I like have a mixture of rubber and water? And what if I have like a continuum of particle sizes between the rubbers and water? Like
What about plasma?
Or what if it's a plasma? Or what if, and do I need to go out and measure every single material in existence to write this down to make this equation? So of course there has to be something more fundamental than this view of, it's just a dissipative view. The trick here is the math will always be more simple if you go back and do the trick that we did with the marble, where you just measure it after and then assign the coefficient and then it works.
Right. Which is what we do 99% of the time.
Yeah. Instead of understanding that and that is like the dissipative view, that I define my shoe as the system that I care about. And then everything just leaving it, I just like assign a term to the stuff leaving the shoe. And I just define a rate, blah, blah, blah. The weird thing about that is that you have to imbue every new object with a sort of infinite and eternal characteristic, which is this coefficient of friction.
Coefficient of friction.
It can't be written down in terms of other pieces it can't be predicted, or it's just one, it's like one hot and cold.
You just have to intuit it.
Yeah. So what I wanted you to think about here, and the reason we bring it up in the book is like, this should start to sound like what the strange loops are, is instead of writing down a fully deterministic set of equations where everything is cohesive, I'm just going to do this little trick where I say, okay, well, I have a system and I know there's other things outside of it, but I'm going to ignore everything else outside of it. I'm just going to have my system. It's going to be a closed system and it's going to have a little bit of self-reference because now I know that there's a thing leaving the system and it depends on something. And so like, I'm going to use this stuff inside the system to define what's leaving the system, right?
Mm-hmm.
That's the strange loopness of it or whatever. And and now we're going to do a big jump and be like, is the universe a dissipative system or not?
Right. Versus,
and
is it a system in equilibrium?
An equilibrium system where in theory we should be able to account for everything if we're using the term universe correctly. Everything is just in it. You just keep making your system bigger until it includes all the things. But what if there are things in there that we fundamentally cannot observe?
Well, we know that there's things in there that we fundamentally cannot observe, right?
We do, right?
It's like the whole idea that there's a speed limit in space is the speed of light. Anything outside of what we 13.8 billion years ago, we can't see.
Right. So from this sort of epistemological view, this theoretical framework that we're looking for to make like a reductive universe, we already have some evidence that it doesn't seem like that's how the actual universe operates. So like, okay, we're leaning more towards the dissipative universe, right? But like just for the sake of argument, let's say, what would it actually take for you to calculate from just the view of the shoe and not knowing anything about the surface that it's in contact with, to calculate with infinite precision the deterministic view of the friction and the dissipative friction leaving? And this is where we get back into the swimming pools and the eggplants and all the crazy stuff that made it seem like, why are we spending time talking about this? Because and initial conditions and the three-body problem and like, what does it mean to be solvable or not solvable? Because if you have an object and we say, okay, I'm going to have godlike knowledge of all of the particles inside of this object, and it's at rest. And now I put a force and I start pushing and the object doesn't move at the rate that I was pushing it, right? Oh, there's energy going somewhere. Okay, that's our dissipative energy. So I'm going to look at all the atoms, look really close, look for gradients on the object. Okay, these ones actually were starting to move, but like the ones at the very bottom didn't move. And so I can like write down these little gradients. Okay, that's where it is. That's where all the energy is going. This is what I'm still I still have a deterministic view. Now, some of those little ridges that are interdigitated, they snap. So you have your first tiny little bit of movement.
It's a crack.
It's like a bunch of little cracks, right, across the whole surface. Those cracks also lead to waves throughout your object.
Whoa, yeah, that's right.
So not only do I have to worry about all the little dips and divots and cracks inside that like we already know is very hard to do. But in theory, you could do it or you could approximate it. Now I have to think about waves bouncing around inside my object,
Causing more cracks.
causing more stuff because at time t equals 3 in my next step, I need to account for whether there's waves hitting that to correctly continue to predict what's going to happen in the next time step. And if the waves are hitting it in such a way that they cancel, that I can't know where that came from the position of that individual atom, that I can't necessarily predict where it was going to be in the next step. Immediately, we have this chaotic system where like, even if I can solve it numerically, I definitely cannot solve this with any of the known math in the universe that we could do. And there's no quantum mechanics yet. It's already starting to look like quantum mechanics, but we might be able to solve it for a set of solutions that are sort of symmetric around the types of waves that fit into the object. And that does start to sound like quantum mechanics because there's like certain allowed energy levels of things that could happen inside of it. But to get even more complicated, what if the waves, the cracking that's happened in those interdigitations is happening such that like the frame rates are not static? So there's a crack here that went pop and it started to pop, and there's one over there that's like still only halfway popping. So now remember how I also have to tune my frame rate to be correct.
Right.
And that was chapter 4. And if the frame rate is off, then I can get the correct representation, or I can get the correct, numerical calculation for point at this point, but I'm going to be wrong over there. So I have to start making like variable frame rates. And if I have variable frame rates, then I can't necessarily predict the waves in the correct way anymore. And like the whole thing just becomes fundamentally incalculable
From a deterministic.
pretty fast from a deterministic view. So then it's like, okay, all of these little tricks, all the things that work, these are all working towards saying, yeah, even an everyday object for something as simple as friction, which you can rewrite any interaction as a friction interaction. Like it doesn't have to actually be a friction event. It's just any time that you're taking a measurement with a big object that is involved with lots of little objects.
Technically, if you touch anything with anything else, that's friction.
Yeah, where anytime that there's anytime that you are making a measurement with something big and you're trying to measure it across a bunch of little things, there's going to be something that looks more dissipative than anything else. And that dissipation is a fundamental feature of measurement, not necessarily of the universe, like of just how we measure. There's a fundamental sort of like dissipation thing that happens if you're trying to measure something really big with something really small, or something really small with something really big, right? Or a bunch of little small things with something really big. And that's the argument that like with reference to the universe, we are the atoms. And with reference to the atoms, we are the universe. We are that far away in space and time. So there should be major dissipation problems. And then the part that I didn't talk about is that the frame rate, like, so say let's inside of the object, say you even buy like the variable frame rate. Okay, but I have godlike power, so I can write down variable frame rates for different parts of the thing with all the different molecules. Okay. Now, I still have to keep track of how long it's been going, and I can't know how the waves are going to propagate necessarily until I've watched a little bit of the movie.
But then if you're watching the movie, then you're not looking at the...
Or put it this way, if the object now that you're in contact with is also under acceleration, so the ground is being pushed away, the fastest you're ever going to be able to like catch up with that is as fast as the acceleration of the other object is happening. And that's the second section now, where we're saying, I call it deduction production, which is like you're measuring a movie while you're inside the movie.
Yeah, I remember you talking about that.
So you're making a movie, but you don't know what it's about yet. So
okay.
How long, right?
Reminds me of the Spaceballs. In the middle of the movie, they start watching the movie and they fast forward it. It goes, is this now? Now? This is happening now. We'll go back to then.
Yes. Actually, when I first thought of this concept was, which this kind of thing comes up all the time in like sound design and production too, because if you want to like do a sound effect, you have to like lag the whole track to get caught up with, if the processing time that it takes to like add reverb to your voice or whatever. I was watching Mr. Show. You remember Mr. Show? Bob Odenkirk and David Cross.
Yeah.
And they had a sketch about something similar to that, where like they're interrupting themselves as the sketch is like is progressing. And it just clicked for me like, oh, the fastest that a causal inference can be updated is the speed of the causal inference. And that is light. That's it. That's what light is.
That's what light is.
It is the fastest that a causal inference can be
Yeah, so
updated.
the ending paragraph of the second subheading, which is deduction production, is what you called it. The final paragraph I circled and just wrote, "What?" So I still don't know if I've fully wrapped my head around it, but here I did take a note here, and I think I want to revisit this just to get your opinion. So I understand that part of the issue is it's the measuring, right? So like a lot of the, we're running into these issues because we're really talking about the fundamentalness of measuring. So I wrote, when we measure something, we don't actually cause the observer effect, but that's an illusion. Is that what you were trying to say?
So,
That
well,
like
maybe you can rephrase your question. Yeah.
so basically, we're not actually causing like, so if you measure a photon and, it acts like a wave, and then you measure it, collapses the wave and we're not actually causing the collapse, is what it seemed like you were saying. It was like, you know, the collapse is happening because of something that happened in the beginning of the Big Bang, but we're observing the collapse of it, but we're not actually causing it. That part is like an illusion.
Yeah, yes. That's a good way to put it, because the causing atoms to behave in a particular way, first of all, is very, very difficult
Mm-hmm.
in a precise way. And what we think we're doing when you like hit a baseball with a baseball bat or something, like you're not really causing atoms to behave in a certain way. You're causing the baseball to behave in a certain way. And yes, you can argue that it's composed of atoms, but you're not making them behave independent of the object that was already like doing certain things.
Right.
So, and the observer effect, I think that's tricky because that's used in Einstein's relativity. And I think you mean more just like
Yeah, just like the act of
the,
measuring, right? Not the observer
yeah,
effect.
like
Sorry.
why is there a human intervention made it decide a thing?
Right. Yeah. I'm
Right? That's
talking
what
more
people
of like
get
the
hung
quantum
up about.
mechanics part, right? Where
Yeah.
it's
Yeah.
like,
Yeah. Yeah. Yeah.
yeah, it's causing, multiple realities because, the electron could have been in 9 different places, but you don't know until you measure it. And then it is in one place, whereas
Yeah.
it could have been, you know, that whole thing.
Yes, it's that in order to understand quantum mechanics from the whole systemic kind of view, we stop thinking of it as a small billiard ball that I shot off in a certain direction. And we have to think of it as like the universe is doing its own thing.
Mm-hmm.
And I can sort of reach in and try to see it at this very small scale. But in measuring it and inferring where it is, I'm actually like interacting with a whole bunch of things I don't really know how to interact with. And that's where the money analogy comes in.
Okay.
Right? Is that yeah, maybe we
Let's
can move on to that.
jump into that because I didn't love your money analogy in the previous chapters, but in this chapter, I actually felt like it came through a little bit better. So let me just read something from the book that I highlighted. I thought it sort of made the point pretty good. It says, asking where the momentum specifically comes from would be a little like calling your bank and asking them to clarify which funds were allocated to you when you requested an electronic withdrawal. It's a malformed question. So basically, I think what you're trying to say is that things like, and I don't think it just applies to momentum, right? This could apply to any fundamental force.
Uh-huh.
But basically, what you're saying is that like trying to account for momentum is kind of like trying to account specific bills for an electronic transfer of money. It's just not how we should be thinking about it. Right. So trying to draw a line between like, oh, momentum came from this atom and is now transferred to this atom and is now transferred
Right.
to this atom
Right.
is not how the universe works. Like
In that
momentum.
causally determined, like
Yeah.
I measured it and then I forced it to choose to be in the upstate versus the downstate or whatever.
Right.
Yeah.
I like that. That to me, the analogy made more sense. And this has more to do with language than I think about the fundamental reality of or
Yeah,
fundamentalness.
that the universe has so much like momentum to spend in propagating itself, right? I think like upon rereading, I think if I were writing this chapter again, I would focus less on the topics about like things happening in the early universe, because it's not necessarily that they were happening in the early universe in like a causally determined way. There is still just like a bunch of, things that are generalized things like charge and mass and electromagnetism and stuff that we, in the same way that we don't, I don't think about like, well, which electron was it? It's like, no, it's just a electron, which is also why it doesn't make sense to get all hung up about, well, which path did it choose? It's like, well, it's not even like
Yeah.
really like one electron. There's like a beam and it's complicated to get the beam to go, and but it is fundamental in the sense that causality at that level is not is no longer a discrete quantity that you can like impart and like pick up and move around
Right.
the way that we think we can here
Right. Like,
in our larger space scales.
yeah,
Yeah.
because like at our level, I can pick up a pen and drop the pen, and I'd be like, yeah, that pen, I picked it up and dropped it, so there's a causal relationship to me picking it up and dropping it. Whereas when you get to the quantum level, that's not how things interact. That's no longer how it works.
Yeah.
There's
And
some new rules in town.
this is, I don't know if this sounds obvious to people. Like Brian Greene, I think I saw a video today of him saying
Who's
that he
that?
doesn't believe in free will because it's all deterministic. And like,
Oh, yeah.
I didn't choose to pick up a pen. There were just laws, there are fundamental laws that I can't break. And so I will always have been going to pick up the pen, and I always will have picked up the pen, and I always will pick up the pen. And it's like, yeah, that's true. But it's also sort of like, sweeping under the rug the fact that we can still make measurements. Like,
Right.
I can pick up the pen and tell you how much it weighs. That's what's interesting, right? Is
Right.
the at the fundamental epistemological level, the act of the measurement is this tangled hierarchical strange loop phenomenon that I have to define two objects as being separate objects when they're really at some deep level they're not. There's just a bunch of atoms that are sort of with a gradients of composition from one thing to the next thing. And at the moment of like picking up the pen or the atomic level, there's really no difference between your hand and the pen. So when I go to make the measurement, that's what's weird, is that I can like have two different objects that can move around at different rates. And that's what makes our universe fundamental. I remember like the first time I ever had this thought, I think I was rowing a kayak.
Oh,
And I just
fun.
could not, and I was watching the water swirl around as the paddle went in, and I just, like, could not understand how you could move the boat with the paddle if the water is not one object and, like, the paddle goes in there, and now it's part of, I just, like, I couldn't
Yeah,
wrap my
you
head
could
around
like
it. I couldn't understand.
see how you're all sort of like in one. Yeah, I like what you're saying. How like at the atomic level, like there is no difference between you and the pen. And, when you're messing around with water, that becomes apparent because the water just sort of
Much more clear.
envelops things. But I like that because for me, whenever people take things from like quantum mechanics, and it's a lot of people like to do it, they take ideas from that and then they apply it completely out of context to something that we talk about, something like free will. You know what I mean? It's like, listen, whether or not the universe is deterministic, complicated, we don't really know. We can't really know. It's, not easy to, try to define it deterministically. And we got to be engineers about it. But even if you do believe in your heart of hearts and you think that like the math shows that it is deterministic, that it's not a thing that you can then turn around and apply to something like free will, because it's just like
Right.
your contexts are totally wrong, right? It's like trying to take something from, you know, the macro scale of like the size of the solar system and apply it to our regular day lives. It's like, nah, you're talking about the wrong context. And that
Yeah, it's
always
inductive bias, right?
yeah, and so it's like, no. So, I mean, I also don't think free will really exists, but for very different reasons. Not because the universe has fundamental laws. It's because I think consciousness is sort of a trick. And they've done studies where they can get people to make decisions with like, they'll influence their decision making and then not tell them that they influenced it and then ask the person why they made the decision. And they will have a very long winded explanation of why they made a
Mhm.
decision. And the reality is we can show, no, it's like actually they probably did it because of all these other influences they didn't even know were happening. So like a lot of our decision making is
Mm.
happening sort of behind the scenes in our brains. Like they can also do MRIs and ask people questions and know what answer the person's going to say before the person says it, because like they can watch
Mm.
the patterns develop in their brains. So to me, that shows that like making a decision is a bunch of different things happening in your brain all at once. But what our brain
Mhm.
does after the fact, when someone asks you to reflect upon why you made a decision, you then come up with a narrative. You
Yeah.
develop a
Yeah.
narrative of why I did something. And it's like that narrative is oftentimes not true. You are
It's
after the
fabricated,
fact
yeah. Right.
fabricating why you decided to do something when you didn't really consciously, you were still conscious, but like you didn't go through some sort of thought process. I think some decisions people do, if you like stop, like really stop and think about something, okay, I did some thinking beforehand, maybe there was a little bit more thought process built into it, but does that mean that like when someone asks you a couple days later why you chose that, like, are you actually going to give a exact, the narrative of what you thought? No, you're probably going to have edited at that point and you're going to recreate it,
Right. And which one is more real, right?
right?
because, maybe, yeah,
That for
maybe
me,
you did.
that was the biggest breakthrough for understanding consciousness of like human consciousness is that our brains are really good at developing narratives and telling ourselves stories. And a lot of what we think of conscious thought is, and I would not necessarily say it's an illusion, but more of a trick. We tell ourselves stories of
Uh-huh.
why things happen and why we did this when reality is far more complicated and we're not actually, that's not actually what's happening. And there's a lot more
Hmm.
things happening around us that we're just editing out. That goes into like get to understanding of like how our brains put together the images of things around us and how like there's huge blind spots right in the middle of your face. You're not actually seeing anything right here, but your brain
The
just fills
optic
it
nerve.
in,
Yeah.
brushes it
Right.
up, makes it feel like it's a cohesive thing. And so you start to sort of piece out like the human brain and like the way that we develop and the way we talk about things, you start to realize, oh, okay, the way we think about reality or the way we perceive reality is actually very much a fabrication that we live in and that we pretend this is how it really is.
I mean, I don't know if it's all a fabrication, but
No,
I think this does we can get into like simulation theory and stuff because I think that
that's been
I think
disproven.
you touched on a really cool point. Well, not sorry, not the simulation theory that no, everybody else talks about, the kind that I have in my head,
Right, right, right.
but which is more like an inference, like a big inference theory, which is like that the universe is big inference. And I think ML actually gives you a new angle to think about this when you talked about how the answer, like the true whatever biological process that led to a decision, is something that you would try to measure via fMRI, right?
Hmm.
The rationale afterwards may or may not be like linked up with that,
Hmm.
but it is the framework, it's the machinery that's developed to try to at least parse it.
Right.
So it's you taking a measurement of your own self after the fact to try to understand what happened.
Yeah, that's a good way to put it.
And
Yeah.
right, it's taking a measurement,
Yeah.
and measurements are hard and they're tricky and they're always so like some of them are going to be correct, some of them are incorrect, and that's just the reality of life. It doesn't mean that we throw out free will because I still think that you can in an everyday quotidian sense because I think you can still like come to a functional understanding of why. And I feel this because I have small children at home. Like, where I'm like, you absolutely can decide to put down the remote and come to me when I tell you what, to like,
Yeah.
you have to be able to do that. And because I'm teaching them to interact with themselves and make that measurement about why they said or didn't do whatever they said, because it's not
Yeah.
always clear to them and it can take a lifetime to
Yeah.
get there.
Gotta love that moment when you're going, no, and they're giving you the eyes like, oh, I'm gonna do it.
Mm,
Like,
mm-mm,
don't
mm-mm,
do
mm-mm.
that.
Yeah. Yeah.
Yeah, no, I think Daniel Dennett put it best when he said that, like, free will may be an illusion, but it's a really useful trick.
Yeah, but
um,
illusion in the sense that, like, you can't write down deterministic laws for it, that doesn't make it not real at
yeah,
all. That's what I spent a whole book talking about. There's
yeah,
all
I
sorts of ways
agree.
that things can be real, but not deterministically, hierarchically composed. And this is a cool segue because I think the way that we've been talking about atoms are tornadoes, your brain is very much a tornado. And I think
Absolutely. It's one of the more
strange loops are very
complicated.
much yeah, like, and so, yeah, you have to look at, and I was going back to the ML, like, I don't know if you caught when DeepSeek first came out, which is like, really changed the way we use AI just in the last 2 years. It performed really, really well. So DeepSeek is this like Chinese model that was a hybrid reinforcement learning with the LLMs. And reinforcement learning is where you say, okay, I've trained my big model. Now I'm going to train another model that knows how to spam the big model to ask it the right question until I get to the right answer. Because like the user's giving me an answer. Now I have this module that's going to say, ask the LLM, check it against other things in the LLM. Doesn't seem quite right. Okay, let's ask again. Okay, let's ask again. Okay, let's ask again. And then like that asking, like the governance of the asking is what's called chain of thought.
Hmm.
And which is another thing you can go look up if you want. There's lots of papers written
So
about
it's
chain of thought.
basically like an AI training or training itself to do prompt.
It's the
It's
query, yeah. So it's like doing its own, it's taking over the prompt. Remember forever we were all going to be prompt engineers, and now it's like,
yeah.
actually we have agents that are better prompt
I
engineers.
figured it's something an AI can do better than a human anyway.
And that's what DeepSeek was. But what was really funny is the first week it came out, if you ask it a question and then and one of the cool things you could do though is it could actually give you the chain of reasoning,
Oh, fun.
which we couldn't ever get before.
Right.
And it was fascinating because sometimes the answer that came out was correct the first time, and then the chain of reasoning was like completely garbage. And you'd go like, it got it right the first time. And then it went, I'm not sure if this is the right thing. And it just like kept going off
And
in
then it
some
went
corner.
roll.
And then and this is when you
That's
start getting
called
really weird.
schizophrenia.
Well, then you get things that look schizophrenic because it's like, I'm trapped. I don't know what to do. I don't know what to do. I don't know what to do. I can't find the answer. And it's like, there's no, it's an illusion in the sense that it seems like it's thinking that. It's like there were all 100 messages came out at the same time of it saying I'm trapped, like.
I mean,
But
there's definitely time in between. If the thing is thinking, if it is a consciousness, then it's just experiencing it much faster.
yeah, true. That's true. That's terrifying. Anyway, we're kind of off in the deep end here, but
Yeah. Yeah, it's fun stuff. I mean, AI is interesting. There's a lot of speculation right now. I think there's a lot of people running scared. There's a lot of alarmists out there talking about, AGI could be around the corner and it could cause a lot of problems and blah, blah, blah. And obviously, I think the thing to remember about that is nobody knows.
yeah, nobody
Anybody who
knows.
pretends to knows is trying to make a buck off you.
It's true.
But
There's a
are
lot
there
of hype.
things to be afraid of? Sure. Any new technology historically, and I think that AI very much the speed at which it's going to change a lot of industries is probably going to cause a lot of heartbreak, cause a lot of problems. A lot of industries are going to have a lot of people looking for work very quickly. That's been an issue ever, for since technologies have been around. New technology comes out. People who used to plow their fields or the plow pissed off a lot of people. They used to do that by hand and they got paid for it.
Yeah, right.
But it's the speed that with the changes and,
I agree with you. I think that we have to be careful about the policy, and I think there's going to be some heartache.
our government's on top of that. We come up with policies so quick these days. They're not too old.
Sure. What was it? The Secretary of Education called it A1 instead of AI. But anyway, what I was going to say is that on a slightly more positive note, I think it's uncovering the most exciting thing about it is that it's uncovering an actual deep fundamental truth about how knowledge is created and produced and cataloged, and how it can be kept and compressed and all these things that we've never done before. And we're going to get there in the book, but a lot of the ideas and stuff can be couched and reformed in terms of information theory, which is like, what's the fastest that a piece of information can be written down and inferred or deduced, and that's where the deduction production is like, okay, well, the fastest thing is if something's changing in real time, then the fastest you're ever going to causally interact with it is that real time, and that's like a teaser to the next section. The question here is, are there dissipative things in the universe that we can look out and understand now? Because if there are, it should, go back to our friction story. It should be that we imbued something with an eternal one hot encode type thing. There should be like a set of things where we go, well, I don't know why, but this thing has this feature, and this thing has this feature, and this thing has this feature. And it just always has been that way, and it always will be that way. And the feature is something that is self-referenced in terms of how we can measure it, right? In the same way that the feature of the coefficient of friction is like, well, it sucks up energy this fast. It's a fundamental feature, but it's defined by how fast it sucks up something not fundamental.
Gotcha. That makes sense.
Right.
Yeah.
And there should be stuff in our universe that appears fundamental because we've given it we've imbued it with eternal feature. Yeah. That if the universe is fundamentally dissipative, then there should be these qualities that we have to just assign that always have been this way, always will be that way. And then the assignments are going to be in terms of things that we can measure. Right. And in our big inference scheme here, it's like basically saying, whenever I try to, because let's say you're inside the shoe now and
wearing a shoe
from
when do we get to shoe?
Still with the friction analogy here.
Right. So I'm inside the shoe.
Now you're inside the shoe. I started pushing on the shoe. I can't know anything that's about the other material. I cannot fundamentally know because it's blocked off to me. That's the term. That's the definition of dissipative. I go to push the shoe and it's not going. And I'm putting this much force and it's still not going. That's where that feature comes from. So it's like, where does the prediction fail? Where does the ideal fail? And it's deviations from ideal. That is where the dissipative thing comes from.
You do talk about that in the book, that basically in our universe, when we get to those points where they fail, because it's a dissipative system, that's where we should be sort of focusing. And those are the exciting moments of where...
They should be everywhere. It should be totally omnipresent. It should be like part of every measurement of everything ever. And it's like, well, is there something like that? Do atoms have like some sort of quality that we just give them, like charge and spin?
Oh, oh,
and,
I see what you did
and
there.
like and like when they get close to each other, they don't act the same way as they would otherwise because of those
Because of
charge and spin features.
friction.
It's the universe friction. It's universal friction. In the same
Right.
way that like gravity is warp space-time,
Mm-hmm.
which is to say that I was going in a straight line and I didn't do anything, and now I'm not going in a straight line anymore. Same with charges that go near each other. They're going in a straight line and then suddenly not going in a straight line. Like there's a way, yes, there's a force, but you could reterm the force acts at a distance, even though there's no particles exchanging momentum between those two things.
So it's the shape of reality.
It's dissipative something. Like it's the calculation breaking down and failing. I don't know what it is. Right. This is what's fun about the book.
Don't say
And
that.
being an author.
We gotta convince people you know what you're talking about. Just kidding.
Fine. Back up. It's
No,
you know,
you're allowed to not know what the solution to the issue
theory
is.
is what I'm asking
Mhm.
in the book. I'm asking, could we think of it this way? Could we think of the fundamental forces as not so fundamental, but actually just being what we sort of naively labeled as fundamental because we were doing a measurement, because we're stuck inside the strange loopy kind of measurement machine.
Right. So in this idea then, say you fast forward a billion years, could the fundamental principles start to change? Is Planck's constant suddenly 2 Plancks?
Yeah, I
Bum, bum,
don't think
bum.
so. And I think
So they are fundamental. You lied to me?
there's a difference between fundamental and unchanging, or like eternal, right? And I think this is where maybe we go all the way back to the Inside a Black Hole episode and just be like, well, because of relativity and weirdness, like the dissipation could be, and also that it's concurrent.
Mm-hmm.
The dissipation can be like omnipresent for forever.
Right. So you
It doesn't,
heard it here first, folks. The universe is dissipative, and that's why there's spin and charge. And when two atoms get close to each other, it's actually the curvature of space-time, of reason that it spins, and they have this force that interacts. It's
Yeah, physicists wouldn't like that, but
it all together.
that way. But let me try to do it closer to the precise language. It would be if we were to get a unification theory, and a unification theory is necessarily the causally determinate sort of view of the universe, then we cannot do it in a way that doesn't account for these fundamental unknowables that would arise from a dissipative system measuring it from the inside out. And so like those should be a feature of the unification theory, not something that you get rid of because you now have all of the pieces that make it up. In the same way that Bertrand Russell thought there was going to be the last axiom, and then Gödel was like, no, the last axiom is that there cannot exist a last axiom.
Yeah.
I'm saying the same thing about cosmology. Like,
Gotcha.
the unification, the linchpin in unification is not going to be loop quantum gravity or whatever.
So you heard it here
It's
first. There is
gonna
never
be-
going to be a universal theory of reality.
No, and that if we did have one, it's going to be focused around measurement and how we make measurements. So it's a relativistic measurement theory as opposed to just the special and general relativity.
Well, that's a good segue into Ilim or Elim.
Ilm.
I had never heard that word before. I like it. I'm going to use it more
Did
often.
you look it up?
Well, you described it in the book. I had a little note here I thought was fancy, I thought was funny. Throughout the entirety of the book, for those of you who actually read Gavin's book, he has these footnotes, which we've touched on before. They make no sense. What are you doing? But that's okay. But randomly in this chapter, for some reason, you start putting things in parentheses behind stuff to explain it. I'm like, no, you had a system going. You would put numbers, and then I jumped to the bottom of the page. Now all of a sudden, you got parentheses in here. Yeah, you put Elim, and then you put a fancy word used by pioneering cosmologists to refer to the soup of plasma that formed just after the Big Bang. So yeah, it's the primordial plasma soup that formed right after the Big Bang. So that's interesting. I never heard that before. I like that. Another thing I thought was funny that you did here is that throughout this book, you understandably refer to quantum mechanics quite a few times. And so far, you'd always just write out the word quantum mechanics. And this chapter is the first time you started just abbreviating it to QM. Which again,
it's like if you made it this far.
Well, it just cracked me up because
you know what that is now.
Most of the time, you're going to establish your acronyms first chapter, get them out of the way, then you just use them. But Gavin was like, I'm getting too lazy. I'm not typing out quantum mechanics every time I got to say it. It's QM, baby. But yeah, it did take me a minute. I actually stopped and I was like, wait, QM? Like, I'm pretty sure that's quantum mechanics. So like, is that something else? But yeah. Anyway, just fun little things. But again, I wanted to highlight how excited you were in this chapter. You would put lots of exclamation points. My favorite was when you put, observe them and understand them. That should help us move forward, stitching together a shiny new epistemology! Exclamation point.
Yeah. Do you not feel like you have a shiny new epistemology?
Just brand new, baby. It's got
sure
that
do.
new epistemology smell.
And honestly, as I've walked away from the material so long, when I come back to it, it really does feel like that. I'm like, oh man, there's
good
a
stuff.
completely different way to think about everything in here.
Yeah. I also do like this idea. I mean, we've hit on it a few times, but it is sort of, I think, one of the tenets of your book, which is basically that like the Big Bang is still happening. And that's why a lot of the spooky stuff happens in quantum mechanics, is because I think you put it best here where it says, they're happening way back in the early universe and just reaching us now. That's a pretty cool idea. I know we've touched on it a few times, but I felt like that was a good. You finished this chapter on that, and I thought that was a cool way to kind of summarize that up. But yeah, it's good stuff. We're getting there. Another thing you do in this book that cracks me up is that every single chapter, you'll touch on ideas and be like, well, don't worry, we're going to come back to that in the next couple chapters. We're going to touch more on this in the next chapter.
And then we never really...
Well, no, I think you do, but it's just funny because I'm now on page 78 and I'm like, there's only like 30 pages left.
There's only 30 pages left. And
we can't touch on too many of these
15
ideas.
things to touch on again.
Yeah.
Well, hopefully I did a good job this chapter explaining, because I felt like this podcast was the first time I was able to touch on almost every single concept that we introduced.
Yeah.
And how all of it is in this one picture of A, the difficulty and how it makes it fundamentally impossible to do this type of calculation.
Mm-hmm.
And B, if that is true, then that should be something that is sort of universally generalizable and applicable. And that's the big aha moment. That's like for me, that was the apple falling on my head kind of thing, was to be like, because in my work, what I do is I run big, complicated simulations, and there is a constant struggle with people who employ more nuanced and more deeper theories of QM, but at the expense of computational power, and other people who want me to simulate bigger and bigger things. So I have to do it less and less accurate. And my whole career, I've been stuck between these two poles of people being like, no, you need to do smaller systems more accurately. And other people being like, no, you need to do bigger systems less accurately. And it just being pulled between those two forces for so long, it finally clicked that everybody's wrong. All of you are wrong. The fundamental problem with this is that even if I had all of that accuracy in all of the size, I would still be missing things that make certain things fundamentally unsolvable. And so then and I was at a math conference actually, and this guy had a theory of cracks. And he was talking about how to do cracks and do cracks, how to do cracks. And he was talking about how writing down a fundamental equation to predict a crack. And he got one crack event predicted in a weird and interesting way. And people were losing their mind. They were so excited about this new type of mathematics.
Math conferences sound weird.
I have some stories there that I won't even, but when I sat down and talked to him at the end, and we had this really fun moment where I'm like, yeah, that's cool. It's cool that you figured out how to do that for, that particular idealized system, I wish. And he's like, yeah, I could never do this for anything bigger than 10 atoms. It's impossible. And I'm like, okay, there you go.
You just proved my book right. You don't even read the book, but you proved it right.
This is before I'd written the book. This was a big part of where the
idea came from.
The ideas were developing, yeah.
Well, that's good. Well, yeah, I mean, really, we can just tell people to listen to this episode only. We touched on everything. You don't need a reason to listen to the rest of it. Just kidding. Go back and
Yeah,
listen
or
to
you
the
could
rest
just
of
read
it.
the book.
Yeah, well, no, that's too much. I've tried that. You need the podcast, Gavin. You need the podcast.
So you would, this is good though. You are getting a deeper understanding through the podcast than you would have through the book. Yeah.
Absolutely. It helps to be able to discuss with the author the chapter right after you read it.
I imagine that would be helpful. It's helpful for me too.
Yeah.
What were you talking about?
Yeah. I
ask myself that sometimes. Yeah.
I'm sure you have to read the same paragraphs over and over like I do.
No, I don't. But that's just because it's like a fun memory association. Like I said, every time it's like, oh yeah, remember that conference when I talked to that guy about that thing?
Yeah, that's cool.
And then I asked him to edit my book, and he said no. Or not edit, but just read it.
Oh yeah, I was gonna say
I can peer review.
Yeah. Well,
he's like, I don't know about cosmology. No way.
Gotcha. Well, yeah, we got 2 chapters left, I think, right? 2, 3, 2.
Yeah. Well, there's one more like meaty chapter, and then I just kind of like summarize like cosmology stories, and it drops off pretty quick after that.
Cool. Yeah, well, there's 2 chapters. That means 2 episodes of this left. We might do a wrap episode, but tune in next time. It's gonna be fun. See you next time. That wraps up episode 6 of I'm Finally Reading My Brother's Book. Today we explored dissipative systems, friction, and the role energy loss plays in shaping both the physical world around us and our understanding of the universe itself. If you enjoyed this conversation, make sure to follow the podcast so you don't miss future episodes as we continue breaking down on the inside of a marble, chapter by chapter. And if you're listening on Spotify or Apple Podcasts, leaving a rating or review is one of the best ways to help new listeners find the show. Thanks for joining us on this journey. Until next time, keep questioning, keep exploring, and we'll see you in episode 7.